Hello everybody, welcome to my channel. It's Sekou Omar Traore from Triple I nouveltech. It's been a long time I haven't made a video, so based on certain reason, but today we are here with a good tutorial. Our main topic is going to be PowerWorld simulator and the low flow studies. So without spending much more time, let's just begin with the different sections. So in order to understand the main idea on what we are going to talk about throughout the whole tutorial, I divide this in different sections, which are 7 in terms of number. First of all, we'll be talking about the history of the PowerWorld simulator, where did it come from, and we'll also describe and give some other definitions, and also we'll talk about the power flow problems and the method how to solve these problems. And for those technique, we'll be looking at Gauss Seidel's technique, Newton-Raphson method, and Fast-decoupled. And sometimes to determine the wide bus, we'll also discuss on the Jacobian matrix, but not in this video, in the upcoming video. And we'll also discuss about the power flow equations and conclusion. Then after, I'll put the reference. Let's begin with the history. The history of PowerWorld. The PowerWorld Simulator Corporation was founded in 1996 with the goal of further developing and commercializing the simulator tools. This software was initially created by a university professor named Thomas Overbyte. Its early version was aimed to teach the power system to a non-technical audience. For example, the people who do not understand engineering stuff, which is power electrical technical word and stuff. So to make it clear for them. But with the advance of technology, there was some kind of development on it. For example, the simulator version 18 was developed to solve complex power flow and virtual analysis in order to predict the real behavior of the network system before its implementation on the site. So it also save human power and a lot of physical work before anything happen. So you can see here we have different screen representing the graphical diagrams in the figure 1. As you can see it from here, this is like control center. So let's try to understand what is power flow. Power flow is a numerical analysis of electrical power in interconnected grid system. It's usually simplify the system and focus on the AC power parameters such as voltage angle and voltage and reactive powers at the normal steady state operation. Low flow studies are important for planning and also for extending a new network. For example, if you are, or maybe if a municipal, or maybe if a utility company is trying to implement new project for a vicinity, they do simulation of the network before the real implementation, as you can see. And I will also discuss a little bit on what is power simulator software itself. Power simulator is an interactive power system simulator package designed to simulate high voltage power system operation on time frame ranging from several minutes to several days. This program also helps engineers to draw up project with a close estimate power demand and consumption value of a new and old vicinities network. As you can see from this figure, we have different zone areas, and you can see there are different grade interconnected here. As you can see, zone 1 and area A and zone 2, and we do have zone B and not zone B, area B, and in zone 3, which are also separate in different color. Here you can see two color different. Figure 2 is representing that one. And let's look at the power flow analysis problem. This is a computation of voltage, magnitude, and phase angle at each bus in a power system under balanced three-phase steady-state condition. As a byproduct, as a byproduct of this calculation, the real power and reactive power can be calculated throughout the equipment, such as power transmission line and transformers, as well as equipment losses. They can all be computed. Diagram description of a typical power system network. Let's just have an example on a 3-bus system which require to perform 3 relations to obtain the voltage, magnitude, and phase angle at bus 2 and bus 3 impedance, which are given at 100 base, megavar base. So this is the figure that I was talking about to have an example. You can see we have 3 different buses here. Literally we have slack bus, PV bus, and low bus. Low bus is also known as PQ bus. We'll also discuss on these 3 elements and all of the variables. Basically, you can see there are 4 variables that are associated with each buses. For example, the P is representing the real power or active power, and the Q is representing the reactive power. The voltage V is represented by V, and delta is the phase angle. Meanwhile, there are 2 power flow equations associated with each buses in this section. Let me just come back so you can see. For example, the bus 2 and bus 3, and even bus number 1, which is also known as slack bus. So in a power flow study, 2 of the 4 variables are defined and the other 2 are unknown. That way we have the same number of equations as the number of unknown. The known and unknown variable depends on the type of bus. Thus, we can classify the network as follow. So you can see we typically have 3 types of bus. For example, slack bus and generator bus or low bus. PV bus is also known as generator bus. What is slack bus? And let's have a brief definition of them. A slack bus is the bus where magnitude and phase angle of the voltage are specified. Usually the magnitude is 1 and the phase angle are like 0, or they might just give you a specific number so you can understand. It's also the swing bus are also known as reference bus. Sometimes you may also hear as a reference bus. Its main function is to inject the power into the network to compensate the system demand and the losses, line losses, for example, transformer losses, and different other equipments, in order to keep the power system in balance. The low bus or PQ bus are bus where active and reactive power are specified. We do know those values. For example, you can see here in our PV bus, you see V3 is equal to 1.03 and P value is like 150 megawatts. So it's already specified. Most bus in typical power flow program are low bus. In our case, it is bus T, as I showed before. And generator bus or PV bus are input buses where real power and voltage magnitude are specified, as you may see here in our bus 3. This is generator bus. I'm sorry, I show you the bus 3 in the previous one. It should be the bus 2, which is low bus here. You can see P and the Q values. So let's move on and try to understand the rest. For example, you can see here such as those kind of example might be generator which shunt capacitor or static VAR system are connected. Another example is a bus to which a tap changer transformer is connected. For example, on OLCT transformer, on low tap changer, they can also say that. So you can see the type of buses and the parameters, voltage, real power and reactive power according to the bus type: slack bus, generator bus, low bus. Let's talk now with talk about the power flow analysis method. There are some common methods to solve the problem, such as Gauss Seidel method, which is to solve the linear system equation. It is a method of iteration for solving linear and linear equation with an unknown variable. This method is very simple and used in a digital computer for computing. Newton-Raphson method is more robust and more accurate when it comes to hard calculation and bus designs. For example, when we have like IEEE bus 6, or maybe more than 6 or 15 or 13 buses, you may see sometimes we have a lot of interconnected grades, so we may need to design a lot of buses. And fast-decoupled methods is lesser bus, but it's also good, not much faster than Newton-Raphson. This is ideal for less complex, challenging low flow analysis. However, both methods are used worldwide. Power flow analysis functions, equations, are basically for power flow analysis. The basic equation for power flow analysis is derived from the nodal analysis equation for the power system. For example, a 3-bus system it can be analyzed in a Kirchhoff current law by using 3 different unknowns, which are I1, I2, and I3. You can see here their value and their formula, where Yj are the element of the bus admittance matrix, Vi are the bus voltage, and Ii are the current injected at each node. The node equation at bus I can be written as I as the following. As you can see, I don't want to repeat all of these one, it might take time. Relationship between per unit and real power and reactive power supply to the system at bus I and the per unit current injected into the system at bus is written as follow. As you can see here, where the Vi is the per unit voltage at the bus. II star is the complex conjugate of the per unit current injected at the bus. PI and PQ are per unit real and reactive power. Therefore, you may see the formula according to the notation. So these are basically what I was supposed to explain you. So this brings us to the end of this tutorial, where we'll be talking about the overview of what we said. For example, the power simulator in the project planning and design. It also enumerates a brief understanding of power flow analysis or low flow analysis, which has a wide range of application in a power system operation and planning. The power flow problem, its formulation, as well as different solution methods. And that's all. So these are the reference that I study about and I'd like to share with you, and maybe you can check out for more. Thank you for watching my videos, and if you like it, thumbs up. Bye, see you in the next video.